Good afternoon, good morning to those on the West Coast and Central America. I'd like to welcome everybody to the next installment of Interface University's webinar series. My name is Roger Frechette. I am a managing principal with Interface Engineering, and pleased to have you with us for the next hour. So for those of you who are not familiar with Interface Engineering, we are a 52-year-old mechanical and electrical engineering design firm. We have roughly 240 employees with offices across the United States in Washington, D.C., Chicago, Portland, San Francisco, Oakland, Los Angeles, and in Honolulu. We are known for our design innovations and our work in the field of sustainability and on high performance projects. This includes buildings as well as master plans, and our work covers a very wide spectrum of market sectors, project types, and geographical location. So today we have a very special treat for you. We have the topic of net zero and net zero, near zero residence projects, and we have two fantastic speakers who are going to take us through today's session. So first of all, I'd like to introduce you to Mr. Kyle Rives, PE. Kyle has a bachelor's degree in mechanical engineering from Virginia Tech. You can see it right there. He's got a banner just to his right so that you don't forget that. He has 16 years of experience. He's a licensed professional engineer. He's a lead associate accredited professional in building design and construction. He is also an associate principal at Interface in our Washington, D.C. office, and Kyle is a team leader and leads many of the D.C. office's residential multifamily projects. And to screen left of him, we have Mr. Craig Burton. And Craig is also a licensed professional engineer, and he has his bachelor's in mechanical engineering from Dalhousie University in Nova Scotia. I'm sure I didn't pronounce that right, Craig, I'm sorry. But he has 15 years of professional experience. He is also a lead accredited professional in building design and construction. He was named by Engineering News Record recently as one of the top 20 under 40 design professionals in the Midwest. And Craig is an associate principal in our Chicago office. So both of these individuals are leaders with our firm, and both have extensive experience working on high performance projects across the United States and around the world. So without further ado, I will turn it over to Kyle and to Craig. Take it away, guys.
All right, thanks for the intro, Roger, and thanks everyone for joining today. I'll quickly go over the course description that'll align with your AIA learning units, which I understand based on your participation in the seminar, you'll receive an email follow-up with that information after the seminar. So today, we're going to go over our recent experience, expertise around net zero energy in residential design. We'll go through strategies and codes that relate to this building type, as well as recent project examples from across the country. Our learning objectives for today are on the screen here. I'll read them to you quickly for those that can't see well. Attendees will learn about different net zero ready code requirements and voluntary certification schemes available across the U.S. market today. Attendees will gain greater insight into why performing homes are important and how they benefit both homeowners and developers. Attendees will come away with a greater depth of understanding about design options and utilizing systems in net zero energy homes. And attendees will learn about wider community opportunities to benefit from net zero energy strategies implemented at a district level. So under that context, we'll go over codes first and how they sort of set the scene and how they're changing. We'll go over voluntary certification schemes that impact or affect residential projects. We'll speak a little bit of electrification of the grid and how that plays into net zero energy homes. And then we'll go over some project examples. And with that, I'll let Kyle take you through. Thank you.
Yeah, well, thank you. So with any project, commercial or residential, we always have to comply with our codes. And when it comes to energy efficiency and net zero buildings, the go-to is the International Energy Conservation Code. And from that point, local jurisdictions may make some amendments or adjustments, but that is the basis for all of our energy requirements and conservation needs. There's some other certifications and programs that also give energy requirements, such as ResNet and things like Verdi and Earthcraft that refer to a HERS index, which rates our energy efficiency in net zero slightly different from necessarily what is indicated for the IECC, as well as energy rating index for different compliance paths, and I'll go over that in just a second. As I mentioned, also local jurisdictions will have their own set of codes or standards that will drive even more energy conservation or net zero desires, such as what we have on there in California. We know that they are very aggressive in their energy conservation and striving towards net zero. So while the IECC is always the starting point, it is not necessarily the only means that we have to comply with. So within the IECC, and we're looking at the latest version, the 2018 version, Chapter 4 in the residential energy efficiency, they actually list 3 different compliance paths that your buildings can take with regards to energy conservation. So the first path, which is putting a prescriptive compliance, makes you go through sections 402, 403, and 404, and the building design must comply with all requirements for those sections. So 402 being building thermal envelopes, 403 being systems, both mechanical and plumbing, as well as 404, which is your power and lighting systems. An alternative compliance path will be section 405. Within that is a performance path, or one where you're going to be doing energy modeling, and maybe you're doing additional energy conservation measures within your building that are going above and beyond code, and you are showing how your building will perform against what is defined as a baseline building there within the code. There also are mandatory provisions within sections 401 through 404 that you must comply with. Some of those are things such as thermostats and controls of your equipment that you have to comply with no matter what path you go down. And then they also indicate the energy rating index, section 406, which again is giving you a different rating criteria for your building performance. Now, a key thing to know is that, again, these are the compliance paths that are written in the IECC, but the local jurisdictions do have the means to amend those. For instance, in Virginia, in the latest version of the codes here in Virginia, they've actually included a 4th compliance path, which indicates that you do all the mandatory provisions and then you comply with a res check against the IECC requirements. And conversely, in DC, they actually have amended this to only have 2 compliance paths for a residential building, one of which is you're doing a performance, you're complying with everything within sections 401 through 405, or you're doing the energy rating index. So again, just a reiteration that the IECC is a starting point, but we always have to check with our local jurisdictions on what the compliance paths and requirements actually are. And then this chart is just showing that over time we're seeing the IECC is driving our energy conservation and our building energy uses to be more sustainable and driving us towards having closer to net zero buildings. It's not a requirement yet, but it is definitely a trend that we see happening, especially here in the past 20 years, where you can really see iterations of the code are drastically making improvements to the energy performance of the buildings, and a lot of that we know is due to global climate change and trying to have a better environment for our future generations.
Thanks, Kyle. I'm going to go through some of the voluntary certification schemes that have been developed and come to market over the last 10 to 15 years. and how they may apply to certain projects. So starting with kind of some definitions to frame the conversation. Zero energy buildings or net zero buildings or net zero energy buildings are largely the same thing, but the consensus is really driven to a definition which looks at source energy on site. That is basically a way to account for electricity or fossil fuels that are combusted on site, converting those to the equivalent source energy, which is back at the point of energy extraction, and then looking at the amount of renewable energy on site that displaces additional source energy. Typically you have to put together a little bit of a spreadsheet to account for where your sources are and what your on-site generation is. For an all-electric building, an electrified building, it's pretty easy because everything just becomes electricity. It's managed on-site. So some of the main drivers that we see that are more and more coming up in projects through architects, but also owners. The 2030 challenge has been around for a number of years now. We're actually getting closer and closer to our 2030 goal of carbon neutral buildings. I encourage you all to do a double check on where your projects are currently sitting. I also encourage you to participate in the AIA 2030 commitment if you are an architectural practice, and participate in benchmarking your buildings against those interim requirements so that you get feedback as to how your design projects, your design efforts are working towards these interim goals to get us and our building stock closer to this net zero energy carbon neutral goal 2030. So two certification schemes that we see as being highly attractive around net zero energy in residential buildings are the Living Building Challenge 3.0, which includes several certifications around net zero energy, and has a rigorous but also comprehensive definition and approach to how net zero energy is accounted for and the systems that are allowed to achieve that. A Living Building Challenge building, for instance, includes no combustion, no fossil fuels on site, which are allowed under other certification schemes. So a Living Building Challenge with a net zero energy definition is truly an emission-free building, whereas some other certification schemes are somewhat lenient on fossil fuel combustion on site. Another certification scheme that we see much more activity in over the last 5 or 10 years is the Passive House movement in the United States, also in Canada under a different brand. So the Passive House movement has largely adapted from the European movement, which came to the United States 20 years ago. And they've moved to more of a climate-specific definition of what a passive house project is. And what that means is that every project is treated somewhat uniquely in performance goals that the project needs to achieve to realize the most efficient use of heating and cooling, ventilation and electricity within that building type and within that project site. So it's a certification scheme that really focuses on making the building as efficient as it can be from a loads management perspective, and then allows solar or other renewables on site to essentially be more effective. And then this is stolen from the Passive House organization, so I can't take credit for the chart, but I think it is fairly helpful when looking at what a minimally code compliant building would be versus some of the other energy efficiency programs or certification schemes that are out there. So a building built to IECC 2012 or 2015 even It's going to have a HERS rating between 70 and 80, which is indicative of the energy efficiency of the building. A building built to Energy Star or later versions of Energy Star is going to have a slight improvement on that. Energy Star has mandatory requirements around envelope specifications and light power densities and ultimately appliances, but it doesn't necessarily get into prescriptive approaches to ventilation or to how the heating and cooling systems are sized. And that's really where Passive House picks up the ball and adds in more comprehensive and, I guess in some instances, limiting to the type of construction type that might go through that certification scheme, and really encourages and largely requires a balanced ventilation approach to the residential and mechanical design, whereas buildings built to code, buildings built to Energy Star, current versions can still get away with exhaust-only ventilation approaches. Obviously, there's benefits to balanced ventilation, but not specifically required. Okay, I'm now going to touch on electrification, how that sort of plays into net zero energy in residential designs, and then Kyle will give you a great example of how we've done that on a recent project. So electrification is becoming more and more of an issue, more and more of an opportunity for net zero energy projects because our electrical grid across the United States is becoming cleaner. And this is a function of, yes, there's more solar and wind going up at utility scale as well as distributed scale, but there's also a shift away from coal, which you can see is the sort of dark gray line on this chart. Coal-fired power plants are being retired and not being renewed, and new ones aren't being built. Natural gas is definitely still out there, but our contribution of renewable energy from this green line is quickly increasing. What that means is that the embodied carbon of a kilowatt hour of electricity from the utility grid is becoming cleaner every year, such that if you build a house that's all electric, i.e. there's no gas heating or gas domestic hot water, every year that building is connected to the utility grid, the electrical utility grid, it will become cleaner. The emissions associated with that electricity consumption, the carbon footprint of that building will become cleaner on a year-on-year basis as the utility grid becomes cleaner. So in terms of a strategy or an approach that has future-proofed emission reduction potential, an all-electric building is really key to the solution. Then looking at sort of residential utility consumption on a quad basis, which is a macro level of energy consumed across the United States. In residential, space heating and water heating are really our opportunities for taking fossil fuels, indicated in purple, out of buildings. And the main approaches there are not necessarily just to put in electric resistance heat, which was the approach in some parts of the 70s and 80s in high-rise construction here in Chicago. Buildings were built with heat by light, so lighting and the commercial office buildings was also providing the heat in the winter. It made a lot of sense, but it's pretty expensive. And what's happened obviously since then is that technology systems have improved immensely, and resistance heating is no longer sort of our starting point. Now we're using heat pump-based technologies to efficiently move heat from outdoors to indoors, and doing that in a clever way. And I'll let Kyle walk you through an example.
Yeah, thanks, Greg. So in taking all of those different ideas and strategies and desires to get to net zero, wanted to talk about a project that is completed design and is going to be starting construction soon here in Arlington, Virginia. It's a group home that is going to be for adults with developmental, physical, and intellectual disabilities, but it is a full-time resident for 5 individuals within this building. It will be operated and maintained by the county's Department of Human Services, and there will always be an individual there on site to assist the individuals living there. But it is still, for all intents and purposes, purposes, it is considered a single-family home here in the Arlington area and is situated within a local neighborhood. So the design of the house, Craig, can we go to the next one here, man? Thank you. So, main goal for this building, outside of it just being the group home, is that it was going to be a net zero ready certification building utilizing the Veridian Earthcraft program. So with that, we obviously have challenges of creating a net zero or near net zero building for the individuals that are going to live there, as well as integrating the building design so that the home fits in with the existing neighborhood and existing buildings therein, as well as having kind of high-end finishes, appliances, lighting, for the operators and people that are living within the building. So with any project, whether it be a large commercial office building or a single family residential home, we always looked at our sustainability approach as having four parts, and trying to drive down our energy consumption of our buildings. So, starting with reduction of energy. So how can we do that? High efficient building envelopes, LED lighting, shading, so that we're able to avoid some of that natural sunlight coming into the building, Energy Star equipment and low flow plumbing fixtures. So all of those reduction strategies are incorporated into our design. Then we look at how can we further reduce our energy consumption via absorption. So in this case, looking at geothermal energy and extracting heat from the ground in order to heat our building, or rejecting heat into it in order to cool. Reclamation, what are we losing? What energy sources are we losing from the building that are just going out to the environment that we can reclaim for our use? So we're looking at sustainable materials, and things such as energy recovery ventilators from our outdoor and exhaust air, and I'll touch on that here and again in a second. And then after we've gone through these three strategies and reduced the energy consumption of the building as much as we can, how can we then generate or produce energy on site to try and then drive us to that net zero desire? And in this case, putting photovoltaics on the roof of the building, is kind of the easy and tried and true strategy, especially when it comes to residential. So again, touching on some of those, are the enclosure having very high R values for our structurally insulated panels and roof, as well as high efficiency glazing, trying to keep our U values of our glass and our doors down low, and our solar heat gain coefficients as well. Looking at our mechanical systems and having high efficiency systems and separating those out such that we can individually monitor and control the temperature, the different levels of the building. In this case, with this design, we have a 3-level building, a basement, ground, and a second floor, and we divided those up and have 3 heat pumps that each one will serve the individual levels of that building, as well as having heat pump water heaters, energy recovery ventilators. So a lot of times with your residential buildings, you're not introducing outdoor air into the building, you're only exhausting, and you're relying on opening windows, opening doors to bring that fresh air in. In this case, we actually want to be able to control and constantly have fresh air circulating through the building. So we are injecting or introducing that outdoor air into the building, and then using the energy recovery ventilators to exchange heat from the air that is exhausting the building and keeping it a neutral building pressurization. As well as looking at our lights, it's a completely LED. All of our lighting is LED. All of our appliances are Energy Star rated. And again, all of these are strategies that we're using to keep the energy consumption on this building low. So we talked about heat pumps. In this case, again, we have 3. We have bedrooms on each level. So again, we wanted to make sure that our strategy for our heating and cooling of the space was to be able to divide those up. I already touched on the energy recovery ventilators. That's a picture of what one looks right there. So again, it's exchanging some heat between the outdoor air that's being introduced to the building as well as the exhaust air that's coming out, and saving some of that cooling and heating load. Heat pump water heaters, again, are great in that we're able to not use the just straight electric resistance heat like you might typically have, but take the heat pumps there, and they could be air cooled, or you could have them a water cooled heat pump as well, tying into our geothermal field. And then the appliances, as mentioned before, all of our kitchen appliances, washer, dryers, everything are all ENERGY STAR rated. So looking at the PV here, so we have it's a flat roof PV system where we have accounted for all of our setbacks as required from the edge of the building, as well as any type of vents, roof hatches, etc. We've maximized the amount of space we can possibly do with our PV structure, and that is going to help to offset our energy production there at the building. We took our PV and ran it through a helioscope model that is able to locally look at not only the sunlight travel throughout the year, as well as shading from nearby structures and trees, and be able to tell us what we anticipate our annual production, in this case 16.79 megawatt hours of production for for this building based off of the PV on our flat roof. So taking that in looking at our energy modeling, so on the top left, we have our energy model breakdown of all of the energy use consumption within the building, from the base case as defined by the energy code for what the minimum requirements would be, as well as what the design requirements and the savings therein of broken down heating, cooling, lighting, our plug loads, so anything that's plugged in. We do have an elevator within this building. Again, it has people with physical disabilities, so we have an elevator within there. Our appliances, laundry, fans, pumps, and all of these are based off of schedules occupancy schedules that we worked out with the Department of Human Services based on their experiences with other group homes here in the area. Taking our comparison of our base case and our proposed case, we had an energy use intensity, which is our energy kBTUs per square foot per year. Our base case was 24.3. Our proposed was 20.3, which does not show a lot of savings, but part of that is just how much the new codes are driving down our minimum requirements for our energy savings. And then our PV generation, we were able to get approximately, offset that by an additional 10. So we're looking at our energy use intensity of our building at sitting right around 10, which obviously is not net zero. Net zero would be 0. We unfortunately, with this, in order to get us the rest of the way, we would have to introduce more PV to the project. We proposed something such as a covered pathway between the building and the driveway, and then doing a carport there and having all PV integrated on that. That would get us the rest of the way to net zero. Unfortunately, it is not within the budget to do that. So we aren't pursuing the additional photovoltaics at this time. However, based off of the requirements of the Viridian Earthcraft program, they don't necessarily look at true, an EUI index as a means of rating a net zero ready building. They use a HERS index, or a home energy rating system. And what this does is it looks at things within the building that are more than just the energy production. It's actually looking at a holistic design and looking at the materials that are also being used in the building. So the Earthcraft certification for net zero ready, which is what the requirements of the project were, or they has to have 10, HERS index of 10 or less. Without the introduction of the PV system, the HERS index is currently sitting at 39, and per Viridian's analysis and review of the project thus far, they feel that we will have no issue with getting below 10, if not getting all the way to a HERS index of 0 once the PV is introduced on the building. So that was just a quick summary of that project. Craig, back to you.
Cool, thanks, Tom. Okay, I'm going to go through a few project examples. This one's a feasibility study we did for a townhome project here in north of Chicago, in Evanston. It is an infill project with a south orientation, so beneficial there for solar for sure. It's 40 total units, laid over 5 buildings. Each building, I think, is 3 or 4 bedrooms, and we were brought in to do a quick analysis to respond to local planning requirement, which had been introduced by the local council, requiring that all new developments demonstrate how they would achieve net zero energy on site. So this is I think a relevant study. The project was not built, so that's the caveat, but I think the approach and the vetting of the strategies is relevant. So to do this analysis, we took one of the townhome buildings, which included 6 different adjacent units. We benchmarked those units against utility consumption for similar types of buildings here in the Chicago region. So based on the Chicago benchmarking ordinance, which has been in effect for about 8 years, there's a fairly good database of energy usage intensity associated with different building types. So the average for buildings built since 2013, so within modern energy codes, is 60.3 kBTU. So we used that as a sort of checkpoint to make sure that our energy modeling and predictions was closely aligned. We built a energy model in BEOPT, and we followed the alternative compliance path, the ERI method that is allowed for under IECC to demonstrate energy code compliance, as well as how we account for net zero energy. The challenge in this project was to not pursue an overall electrified solution, but to stick within the developer sort of pro forma of conventional utilities, conventional equipment, but work within the performance ranges that those existing types of equipment have. So looking at the most efficient condensing gas furnace, the most efficient split air conditioning system, et cetera, et cetera. So trying not to upset the development pro forma, but understand what is possible within that context. So this is our sort of IECC compliant performance specification. And if you're thinking about this as an energy modeler, this is kind of like your marching orders. These are your inputs to the model. And then we identified, in collaboration with the design team, what are some high performance measures that we can achieve still within that building type, that construction type. So improving walls, ceilings, roofs, insulation, really getting the best quality double glazed window that we can procure at the time. Some focus on infiltration, and then really hitting the HVAC hard. We looked at 2 different options, one with a standard efficiency solar panel, and then with a premium efficiency solar panel. So typically on net zero energy projects, especially single family homes or residential projects, you're going to be filling up the roof with solar panels. And depending on if it's a 1 or 2 story building, you may need additional space than what's on the roof, or you may need to go to a more expensive solar panel. So the most efficient from a cost and project deployment perspective type of panel is going to be more of a commodity grade panel. But on these projects where we're trying to do more with less space, we're constrained, we often go into a more efficient, a premium grade panel. So we looked at those 2 and tried to evaluate where we needed to be. So this table rattles through each of the ECMs, the model runs, and then we bunch together the measures in a low, a medium, and a high cost bucket to better understand which or what level of performance we can get to with kind of out of the gate efficiencies. The medium cost being like this is going to be a bigger value decision, and the higher cost items being this is likely something that wouldn't fit within the budget. And what we determined at the end here is we went from a baseline. So before we made any efficiency measures, a baseline EUI of 62. With low-cost measures, we reduced that by 8%. Medium-cost measures, we reduced that by 24%. And high-cost measures, we reduced that by 30%. So that aligns with a lot of the modeling and analysis we've done in the past, where you don't necessarily change your building design approach, like going down a passive house route, and you try to stick within the familiar technologies and approaches that exist in the market today. About a 30% reduction is what we see is quite easily possible. Then looking at the solar contribution to get us towards that net zero energy mark, with the standard solar panels, we were able to get up to 85% source energy reduction. So that leaves us a little short. And then with the premium efficiency panel, we got up to 100%. This chart, for whatever reason, shows 99%. That's just me not digging up the right information for the presentation. Okay, so that was, like I was saying, kind of a conventional building type. What can we do within that building type to achieve net zero energy? Here's a different building type where it's a single family home. It's a homeowner that has a deep interest in energy efficiency, in sustainable design, in electrification of the grid, as well as grid resilience and autonomy. So this project started with a passive house as kind of the design mantra, and it is going for certification under the FEIS 2015 certification program. One thing to note about FEIS is that it is a performance-based standard. So while they have suggestions as to this is what we anticipate exterior wall R values and roof R values and amount of glass is, it's really up to you as the designers to demonstrate that through energy modeling, as well as your specifications and verification on site. So this image actually shows a fair amount of glass, but that glass was carefully placed and selected. The shading from this overhang is carefully designed to meet those requirements of passive house. From an MEP perspective, there's a large focus on the electrical systems, and that's what we got more heavily involved in. From a mechanical perspective, there's this project relies on the classic passive house model, which is a balanced ventilation supplied through an energy recovery ventilator. One challenge that we were given is how do we maximize the amount the usage of direct current power on this project, and I'll go into that a little bit more and how that sort of manifests itself. So this is a snapshot of the WUFI model, some of the heating demand, cooling demand limits. So you can see here that to get certification, you have a hard limit on the amount of heat or the amount of cooling you can use during the year. And then similarly, the peak heating load and the peak cooling load that the building can see. These are some drawings of the mechanical system, so showing you that in a passive house certified project, it's critical that you get outdoor air supply and return distributed through the building, and you're supplying to rooms where fresh air is needed, and you're exhausting from rooms where exhaust air is needed. So in a passive house project, your kitchen and your bathrooms become your exhaust rooms, and your living rooms and your bedrooms become your supply rooms. And that's really sort of the starting point for that project. We have a large rooftop array. It's about 10 kilowatts on the roof, and that covers on an annual basis our estimated annual energy usage. The approach with the solar on this project was not necessarily just to generate solar and feed it back into the grid, unless it was needed on site. It was to maximize the amount of solar that can be stored on site and then reused on site. And that's not a requirement of really any of the certification schemes that are prevalent in the market today. But it was a desire of this project to really minimize the demand or the need for utility supply, and maximize the ability of the homeowner to operate autonomously from the grid, and during a grid outage to maintain a quality of life and operation that wouldn't otherwise be possible. So this is sort of the arrangement we came up with on the power side. So in a conventional solar and battery system, the solar is generated, it's a direct current source. It passes through an inverter. The inverter puts it into an AC panel, and the AC panel distributes it in the house. In a traditional AC coupled solar and battery project, some of that AC power is then fed into a battery, which has an inverter to invert that power back to DC to be stored in the battery. And then when you want the power from the battery, you have to push it back through that inverter to convert that DC power back to AC. Then that's distributed in the house to be used by something that's demanding power. Typically in a home built in the last 5-10 years with LED lighting and electronics switching to DC power within behind the plug. A lot of that is DC load. So one of the main charges we had here was to identify a path and a system specification that would allow for a DC coupled use of that net zero energy solar from the roof into the DC batteries and then back out to DC loads, skipping some of these conversions that effectively just waste energy and reduce the amount of electricity you can harvest from your solar system. Here's just a quick sort of math equation that shows some of the losses associated with power that you gain from the utility, and then power you're able to use at an LED light, for instance, when distributing it as AC power. So because you're going through these drivers, being the main one, you're losing about 20% of the electricity that you paid for, versus a DC building having a DC source or an AC source, sorry, and a DC light fixture. Without that driver, you're saving about 5% of the energy. With a microgrid, a DC microgrid, your source has changed from AC to DC, and all of a sudden those losses get larger, and your benefit to going through a DC typology gets larger. And that really factors in when you're looking at electricity that's being generated from your rooftop solar and then being stored and then reused on site. So all of those conversions from DC to AC and back to DC end up penalizing what your net zero investment on the roof is able to achieve. And I just point out that LEED now has a pilot program available for projects that are pursuing LEED to look at and assess and quantify the improvement that comes with the DC power distribution. Then the last example is a project in Fairmont Heights in Maryland. This is a microgrid community project that we worked on. It's in construction currently. It is a collection of 6 homes built by an affordable home developer in Maryland. Each of the homes have been designed to the Department of Energy Zero Energy Ready Homes specification, which means that they don't necessarily meet all the requirements of Passive House. If you remember that comparison chart we showed you before, but they do meet about 75% of the requirements. And what's happening in this project is that the developer is building out the homes to this net zero energy ready specification in a partnership between the utility company, Pepco, and a technology provider of microgrids are deploying this microgrid technology and also the solar panels that will be installed on the roofs. And what the microgrid is achieving is the connection of all the homes together to a central controller and distributed battery resources, which allow for all of the buildings to contribute to a community microgrid, which can store, share, and manage power between the homes. And it's a pilot program, but the intention is that it can be just scaled to different jurisdictions. And what it allows for is islanding. So this microgrid can operate independent of the utility grid. It can distribute DC, direct current power, between the solar panels and the batteries, and then back to the homes. We did hit an obstacle here with the utility regulation legislation that's written around metering of power sources to homes. I think that's sort of where technology and innovation start to hit against what's been written and agreed and voted upon. In this jurisdiction, there's no standard that's been approved or vetted by the utility companies and the ratepayers that feed into legislation that is approved on how utility companies get compensated for their investment. There's no mechanism for utility companies to sell direct current power back to homeowners. So for that reason, we've set up the homes electrically to be able to use DC power, DC lighting, DC receptacles, the ability to have DC appliances installed, but they're not going to receive a DC power on day one. It's going to be an AC utility feed to each of the buildings. And then I guess, sorry, I should have shown this really a little context about where some of those inefficiencies from AC exist in residential homes versus where the DC loads and sources are coming from, and some of the distribution means that we see in these projects. And that wraps us up for the presentation. I think we've left a few minutes left for Q&A, so we'll be happy to answer questions in the chat. There's 2 or 3 that I answered already. I'll go through those for people that aren't reading, but is there a webinar available? Yes, the webinar will be posted on our website, interfaceengineering.com. And there's a number of other webinars that we've made over the last 1.5 years that are available there for your perusing. I'd be happy to share. Second question, is there a net zero commercial certification program available? There certainly is. Both Passive House and the Institute for Living Buildings, both cater to commercial and institutional buildings as well. And I think LEED now has a certification scheme as well that feeds into that. I will let Kyle speak to the third question. Kyle, the question is, why didn't you consider GHE or radiant cooling heating systems, which would reduce the energy consumption in the building?
Yeah, so for the group home, as mentioned, it is owned and operated by the Arlington Department of Health Services or Human Services. So they have multiple group homes within the county that they run and operate. And so the desire from them was to have systems that are similar between those homes, so that way their facilities team can easily, maintain each of those buildings. So while yes, you're correct that radiant cooling or heating systems would have been more energy efficient, it would drive down our energy usage. Based on those discussions, the owner was comfortable with staying with heat pump systems and integrating those into the geothermal field that we're putting beneath the backyard. They also had some discussions with them regarding specific manufacturers, because they also are pulling the controls and monitoring all the equipment back to a central BMS system that monitors all of their buildings and their facilities. So there were some requirements that the owners had for us that we needed to kind of stay within, while also trying to get as net zero, as close to net zero as we possibly could. And then Craig, I think the last one, the next one, in a passive house, are the ventilation ducts insulated within the building envelope? I'm not as familiar with passive houses, maybe you are.
Yeah, well, the requirement is that ductwork is within the building envelope. So, placing ducts or the energy recovery ventilator outside of the building envelope comes with a penalty. Whether the ductwork inside the thermal envelope is ducted, that is, I don't think necessarily dictated by Passive House, but is a function of whether the ERV, the DOAS unit, depending on what type of ventilation system you have, is doing conditioning of the air, or if it's just doing an exchange of supply and exhaust. If you're conditioning your ventilation air, or dehumidifying it, drawing it, anywhere close to the dew point, mechanical code will require that you have that ductwork insulated, depending on where it is located in the building. So it's probably an indirect way of answering your question that it depends. Typically, ductwork, supply exhaust ductwork inside of a Passive House building is not necessarily required. Let's see, is geothermal installation for a single home significantly less cost effective than one for a group of 6 homes? Have you been able to draw any general conclusions on this kind of scaling relationship for geothermal and or other systems? So for the other systems, that's really the premise behind the microgrid study that design that we're doing in Maryland. We've gone on, we have another project in Vermont that's 3 times larger, a much larger microgrid installation, and we're currently in that sort of pricing vetting process currently. I will tell you that for both of those projects, the primary driver, from a benefit, is not necessarily the developers, it's the utility company, and the utility companies are having to comply with obviously emissions reduction targets, but also managing their utility grid, and with the larger, wider scale deployment of distributed solar, central generation as well as on homes, utility companies are struggling, I guess, to find a path, a mechanism to be able to predict and control peak demands. So for both of those projects, the primary driver from the utility company's involvement is this a mechanism that they can invest in, deploy in larger scale communities, and be able to manage loads within homes, battery and solar deployment in order to avoid putting in more electrical infrastructure as people move away from gas. And that's kind of where that math problem will be solved. So it's going to be not necessarily what's the first cost, it's what's the avoided cost that we as utility providers are going to not see by making this investment. And ultimately, that's the same technology largely that homeowners or developers would be putting in to make a net zero energy home. It's just taking it, and monetizing the potential benefit in a way where there's hard infrastructure and ownership.
Yeah, and I'd say with regards to the geothermal part of that question, we're seeing more and more geothermal for single-family homes. I think people are seeing the benefits of it, and then the technology and ease of installation is becoming much more common. So, whether you have a single home or a group of 6 homes, it comes down to, are you doing everything at one time? Or is it a planned community? That's going in where all of the homes are going to be driven off of one, central field, or is each home going to have its own kind of borehole or bore field behind the house, to where you're going to be installing everything at the same time? For the group home project, the loads on the building are approximately 6 tons of cooling needed between our for our heat pumps there. So we were estimating that we would need about 4 boreholes that would be in the backyard, about 1.5 tons per, and those would all be spread about 20 feet apart on center there in the backyard. A lot of that, the actual capacity, and size of the bore field will be done off of conductivity tests that have to be done at the site. How much bedrock are you hitting? Where's your water table, to be able to figure out what the heat transfer there is. So, for that site in particular, and for any geothermal site, we would want there would recommend for that connectivity test to be done early on before the project actually gets rolling. We'll be able to then figure out exactly what our heat transfer rate is there at that specific site, and then and how deep those boreholes actually can go. So where we're anticipating once that connectivity test is done, if we're at a really great site, that could be that we're able to get 2 tons per borehole, or maybe even more, and be able to reduce the quantity that's there.
Yeah, I'd add to this, and this is something that neither Kyle or I were intimately involved with, but are knowledgeable of. Interface has worked on a project in Texas with a housing developer there, and our work is focused on the geothermal field installation, and the way that developer has gone into that community. It's hundreds of homes that are built in phases. For several of those phases, they put in a single borehole with each home, and that borehole, provides heat rejection and injection into, to support a water to air heat pump in each of the homes. But each borehole is then connected to the adjacent borehole in a loop. So basically, as the developer builds out the development, they're building out district heating, condenser water loop to connect all those boreholes together. And what that allows is, to answer someone's earlier question, you don't necessarily have to put in all of the capacity for one home in each home. And because there's a diversity in use and demand, you can actually realize fewer boreholes for the ultimate goal of heating and cooling the community. Because everything is interconnected. Whether that makes sense financially, I think there's benefits to it. There's also challenges with the time you're paying for infrastructure. There's a little bit more pipe in the ground. There's controls, but it does offer some more flexibility in how that technology is deployed. So that's something that we're pushing for on other larger scale single-family home residential deployments. Okay, so I think we've answered from Zachary and Peter. Hey, Peter, how are you? What system is beneficial to create domestic hot water for net zero energy houses? I'll let you answer that, Kyle.
Yeah, I think it depends on what other systems are you implementing. I mean, there again, as we mentioned, there's the heat pump water heaters, which for your domestic hot water, which is acting, more or less like a heat pump for your air conditioning, where you can sit there and rather just be electric resistance, it's using the refrigerant in rejecting heat either to the air, or you can, some can connect back into geothermal. They can also be integrated where some of your rejected heat from your heat pumps, for your heating and cooling, can actually go to the domestic hot water and help to offset some of the heating needs there by tying those systems together. So again, I don't think there's a set answer. It kind of depends holistically on what else you're doing in the building, but we are seeing more of those heat pump water heaters are becoming more common. Costs are going down. Anything that we're looking at for these are not systems that are strictly commercial. I mean, you can go to Home Depot and get a heat pump water heater there and have that installed at your house, just as a retrofit if you wanted to.
Yeah, I would just add that within the heat pump water heaters, there are different types of systems. Some are hybrid, so they have a heat pump section to it, but there's an electric coil as well to top up. There are some systems that are mostly European that are fully heat pump. They don't require an electric immersion heater. It does depend on where you're going to install this, where you're getting your air from for heat injection or extraction. So there's a design consideration that goes into that. There are also heat pump water heaters. There's one manufacturer specifically that makes a CO2 based split unit. So you have your heat pump water heater inside your thermal envelope, and then your condenser is located outside, similar to a split air conditioning system, and it uses CO2 as a refrigerant between the outdoor unit and the indoor unit. That's very popular amongst the passive house movement because Obviously, it gets away from some of the problems that you get into with refrigerants, global warming potential, et cetera, and stick with something that's a little more benign. And then there are other opportunities, like Kyle said, with integrating sort of wider system concepts, like with VRF or something off the geothermal field.
And there's a question, are geothermal installs using wells or trenches? The geothermal, there's multiple strategies. Typical vertical wells are kind of the most common install, but you can, if maybe you have a large, high rocky area, you can't get those boreholes very deep. You do have the ability to do horizontal or coiled distribution, which obviously does not go as far down into the earth, but requires more square footage that those coils of piping are going to be under the ground. And so a lot of times we're not going to have that within a backyard of a single family home or a community. So the typical vertical boreholes are the most common installation.
I would put that answer, Kyle, in the same frame as when I mentioned standard photovoltaic versus high premium photovoltaic. They both can provide the same result. It's just one is typically going to be more expensive or harder to integrate in a project than the other. So horizontal, I think, go in when it doesn't make sense to go deep because it's cost prohibitive and you have the space. But often, you're using vertical boreholes because you're space constrained. You're maybe in an urban or a less greenfield site, and you've got to work with what you have. Anyway, I think that's up to 12 points for my time.
Yeah, I think that's a good stopping point. Craig and Kyle, fantastic job. Thank you very much. Extremely informative. I love all the case studies. And I'd like to thank everybody who took the time out to participate today. If any additional questions come up, please do pass them along. We'll be sure to provide answers. And again, if you are in need of AIA learning units, certificates will be provided to all. So thank you very much, and we look forward to seeing you in the new year. Have a great day.
Thank you.